Humanity has always carried within itself the unease of not being alone in the vast universe. Since the most ancient times, when our ancestors raised their eyes to the night sky filled with stars, this overwhelming feeling of smallness and mystery imposed itself. Constellations served as maps, calendars, and even as settings for myths and legends. In every culture from different eras and regions, narratives emerged about beings inhabiting beyond Earth, from divinities to creatures descending from the skies. This fascination is not merely imaginary. It is born from the innate human curiosity to understand its place in the cosmos and the possibility of not being the only conscious life form to contemplate the infinite. With the advancement of science, this ancestral curiosity gradually transformed into rational investigation. Modern astronomy began to unveil the immensity of the universe, revealing that our galaxy, the Milky Way, contains hundreds of billions of stars, and that beyond it, there are trillions of other galaxies. This multiplicity of worlds made the question almost inevitable. If life flourished on a modest planet like Earth, why would it not have arisen in other corners of this vast cosmic ocean? Reflection on this question gained increasing relevance as we discovered that the chemical elements essential for life, such as carbon, oxygen, and hydrogen, are abundantly present throughout the universe. The transition between myth and science opened space for new ways of confronting the mystery. In the 20th century, speculations about extraterrestrial life intensified with the rise of astrobiology, a discipline that seeks to understand how life can emerge and develop in environments different from Earth. At the same time, the evolution of radio and communication technology allowed for the creation of the first projects in search of signals from intelligent civilizations. The idea that we could not only imagine but actually detect another intelligence transformed an ancient philosophical question into a tangible scientific objective. It is in this context that the Drake equation emerges as a bold attempt to quantify something that seemed intangible. More than a mathematical formula, it became a symbol of the human desire to calculate the probability of the existence of other civilizations capable of communication. By considering factors such as star formation, the existence of planets, and the possibility of life, the equation does not provide a definitive answer, but it forces us to organize our thinking before the cosmic vastness. It is an invitation to reflection and exploration, connecting science, philosophy, and imagination in a single axis of curiosity. The history of the Drake equation is deeply connected to a moment of scientific and cultural effervescence. At the beginning of the 1960s, humanity was experiencing the so-called space race, marked by the technological rivalry between great powers and the relentless pursuit of surpassing limits never before achieved. Satellites were already orbiting the Earth, probes were being sent toward the Moon and neighboring planets, and for the first time, the real possibility of exploring space seemed within the reach of human hands. This environment of rapid discoveries brought with it an inevitable question. If we can advance so quickly in our technology, why not imagine that other civilizations in other worlds may have already reached or even surpassed these achievements? It was in this context that a young astrophysicist named Frank Drake stood out. Trained at Harvard University and later a researcher at important observatories, Drake had a particular unease: the search for intelligent life beyond Earth. In 1961, he was invited to organize a pioneering meeting at the National Radio Astronomy Observatory in Green Bank, in the United States. This meeting would bring together some of the leading names in astrophysics, biology, and other fields that together could seriously think about the possibility of the existence of extraterrestrial civilizations. Drake realized that the meeting needed a structure to guide the discussion, a sort of framework that would organize the numerous variables involved in the problem. That is how he proposed a formula, simple in appearance, but profound in scope. The idea was not to reach an exact answer, but to create a reasoning framework that would allow scientists to debate more objectively what until then had been mere speculation. This formula would become the famous Drake equation, composed of 7 interconnected factors, which, when multiplied, would offer an estimate of the number of detectable civilizations in our galaxy. The Green Bank meeting was historic. Among those present were giants such as the astronomer Carl Sagan, who would later become one of the greatest science popularizers of the 20th century. The atmosphere was one of enthusiasm and intellectual boldness. For the first time, the possibility of intelligent life beyond Earth was being discussed not as science fiction, but as a legitimate scientific question. The Drake equation, when presented, did not intend to provide definitive answers, but rather provoked everyone to reflect on the greatness of the universe and on the small window of time that we occupy as a technological civilization. That moment marked the official birth of a field of studies dedicated to the search for extraterrestrial intelligences. The Drake equation became not only a tool, but also a symbol of the scientific courage to face one of the most fundamental questions of existence. In the following decades, with the advancement of astronomy and the discovery of thousands of exoplanets, the equation would acquire new outlines and interpretations, but its essence would remain the same: to organize our ignorance into a path of rational investigation. The Drake equation did not arise to be a mathematical formula in the strict sense, intended to provide an exact or definitive result. Its initial purpose was much more conceptual, to create a mental framework that would help transform the discussion about extraterrestrial life into a subject open to scientific study. Frank Drake wanted to show that the question, "Are we alone in the universe?" could be broken down into smaller elements, each of them investigable independently. Instead of treating the issue as an immense and unreachable whole, he proposed dividing it into parts, establishing parameters that science could measure, refine, and update over time. This organizing character made the equation a powerful instrument for scientific thought. It functions as a map of hypotheses, in which each factor represents a stage of the cosmic process that could lead to the emergence of an intelligent civilization capable of communication. From the formation of stars to the longevity of technological societies, the equation invites researchers to reflect on which stages are abundant and which may be extremely rare. In this way, it does not provide an answer, but structures the questions, encouraging the search for observational data that little by little may fill each variable. Another fundamental aspect of the equation's purpose is to stimulate interdisciplinarity. No isolated branch of science could answer all the variables. Astronomers study the formation of stars and planets. Geologists and chemists investigate the processes that lead to the emergence of life. Biologists analyze the evolution of intelligence. Sociologists and historians may reflect on the risks of self-destruction of civilizations. Thus, the equation became a meeting point between different fields of knowledge, uniting perspectives that range from astrophysics to philosophy. Beyond its scientific value, the Drake equation also holds a profound cultural and philosophical dimension. It forces us to look at ourselves as a species and to consider our fragility in the face of the vastness of the cosmos. If the result of the equation is optimistic, the universe may be full of other intelligences, which relativizes our position as unique. If the result is pessimistic, perhaps we are a rare and precious exception, which makes the responsibility of caring for Earth and for our own survival even more urgent. In both cases, the equation broadens our awareness and redefines the meaning of our existence in the universe. The Drake equation may seem at first glance like just a multiplication of symbols, but in fact it represents one of the most ambitious efforts of science to organize our ignorance in the face of the question of extraterrestrial life. Frank Drake conceived it as a sequence of factors, each one corresponding to a necessary stage for an intelligent civilization to arise and be detected by us. When multiplied, these factors would give us an estimate of the number of technological civilizations existing in our galaxy, the Milky Way, capable of emitting signals that we could capture. The structure of the equation is composed of 7 main variables. The first factor is related to the rate of star formation in our galaxy. It is the foundation of the process, because without new stars, there would be no planetary systems, and therefore no possibility of habitable worlds. The second factor considers how many of these stars have planetary systems, remembering that until the 1990s, we had no direct confirmation of any planet outside the solar system. The third factor refines the analysis even further, estimating the average number of potentially habitable planets in each stellar system. The following factors deal directly with life. The fourth parameter seeks to determine on how many of these planets life actually arises. The fifth evaluates in how many of these cases life evolves to reach intelligent forms. The sixth factor considers how many of these intelligences develop technology capable of being detected at great distances. whether by radio waves, laser signals, or other means. Finally, the seventh factor concerns the longevity of these technological civilizations, how long they remain active and visible before disappearing or becoming undetectable. This cascading structure, in which each variable depends on the previous one, shows how the equation combines science with uncertainty. Some factors, such as the rate of star formation, are relatively well known. Others, such as the probability of life arising, remain almost entirely speculative. The beauty of the equation lies precisely in this contrast. It clearly shows us which answers we already have and which we still need to seek. More than numbers, the Drake equation is an invitation to exploration, reminding us that each advance in astronomy, biology, or technology can change the result and bring us closer to the answer to the question that has accompanied humanity for millennia: are we alone in the universe? The first factor of the Drake equation is the rate of star formation in our galaxy, a fundamental parameter, since the entire process of the origin of planets and eventually of life depends on the existence of active stars. Without them, there are no solar systems, no sources of stable energy, and therefore no scenarios for the flourishing of civilizations. This factor seeks to answer how many new stars are born in the Milky Way over a specific period of time, usually considered as 1 year. Estimating this value means diving into the complex dynamics of stellar birth, which takes place in gigantic clouds of gas and dust scattered through space. Stars form in regions known as nebulae, places where gravity causes interstellar gas to compress until it reaches densities sufficient to ignite nuclear reactions in its core. These cosmic nurseries, often visible as beautiful fields of colors in the sky, are the cradles of future planetary systems. Currently, astronomers estimate that, on average, between 1 and 10 new stars are born in the Milky Way every year. This variation results from the different methodologies used in measurements, but even the lowest values show that our galaxy continues to be a dynamic and fertile environment for the creation of new worlds. It is not only a matter of the number of stars, but also their quality in terms of habitability. Very large stars, such as blue giants, have short and unstable lives, which makes the emergence of complex life in their systems unlikely. Smaller stars, such as red dwarfs, live for trillions of years, which could offer enormous windows of time for the development of life. However, many of these dwarfs are prone to violent eruptions that can sweep away the atmosphere of nearby planets. This shows how the first factor of the equation is not just a raw number, but a piece of data that needs to be interpreted within stellar diversity. The rate of star formation gives us the foundation upon which all other factors of the equation will be built. If the galaxy was sterile and inert, without new stars, the chance of planets and life appearing would be zero. But the fact that we have hundreds of billions of existing stars and millions born over the past billions of years suggests that the conditions for planetary systems are widely distributed. It is from this cosmic foundation that the Drake equation begins to rise, leading us to the next step: understanding how many of these stars actually have planets in their orbit. The second factor of the Drake equation seeks to determine how many stars have planetary systems. That is, how many of them are not alone in space but are accompanied by planets orbiting around them. This factor is crucial because even if the galaxy is fertile in stars, that alone does not guarantee the formation of worlds capable of harboring life. For much of the history of astronomy, it was believed that planetary systems might be rare. Until the end of the 20th century, there was no direct confirmation of the existence of planets outside the solar system, and many theories suggested that the processes that formed the Earth and its neighbors might be extremely rare exceptions in the cosmos. This view began to change radically in the 1990s, when technology became capable of detecting small movements and variations in the brightness of stars caused by the presence of orbiting planets. The first confirmed exoplanet was discovered in 1992 around a pulsar, a highly dense and unstable neutron star. A few years later, in 1995, the first planet orbiting a Sun-like star was detected, named 51 Pegasi b. These milestones opened the door to a new era of discoveries, showing that planets were not an anomaly, but a common phenomenon. With the launch of the Kepler Space Telescope in 2009, astronomy took a gigantic leap. This observatory was designed specifically to identify exoplanets using the transit method, detecting small drops in brightness when a planet passes in front of its star. The results were impressive. Thousands of worlds were confirmed, and tens of thousands of candidates were catalogued. These data transformed scientific perception, indicating that practically every star in the Milky Way has at least one planet in orbit, and many of them host complex systems with multiple planets. Today, the estimate is that there are more than 100 billion planets in our galaxy, distributed in systems that resemble or even surpass our solar system in diversity. This means that the second factor of the Drake equation, which was once seen with great uncertainty, is now considered highly positive. The discovery of giant gas planets, rocky super-Earths, and worlds in habitable zones has further expanded the horizon. The idea that planets are almost as common as stars has become a consensus among astronomers, reinforcing the notion that the universe is a vast laboratory of possibilities for life. The third factor of the Drake equation seeks to answer one of the most intriguing questions of astrobiology. On average, how many planets per star with planetary systems have conditions to be habitable? The word habitable in this context does not automatically mean that the planet is covered by forests, oceans, and complex life, but rather that it presents an environment where life, as we know it, could at least arise and develop. The most widely used criterion is the presence of liquid water, a fundamental element for the biochemical reactions that gave rise to life on Earth. The central notion here is the habitable zone, also called the Goldilocks zone, in reference to the children's tale in which something must be just right. This zone corresponds to the distance range around a star where the surface temperature of a planet is not so high as to evaporate all water, nor so low as to freeze it permanently. In the case of the Sun, this region extends approximately from Venus to Mars, although additional factors such as the presence of an atmosphere, chemical composition, and geological activity strongly influence the real habitability of a planet. Recent discoveries of exoplanets have considerably expanded our view of this factor. Worlds like Kepler 186f, located about 500 light-years away, or TRAPPIST-1e in a stellar system with 7 planets, many of them in the habitable zone, show that not only do rocky planets exist in favorable positions, but also that they may be more common than we imagined. The presence of detectable atmospheres, potential oceans, and even chemical signs that could indicate biological activity are subjects of intense study in modern observatories. However, habitability goes beyond mere orbital position. A planet may be in the right zone but sterile if it lacks a magnetic field, if it suffers frequent eruptions from the central star, or if its atmosphere is inadequate to retain heat and water. On the other hand, worlds outside the classical zone may harbor subsurface oceans kept warm by tidal forces, as is the case with icy moons in the solar system, such as Europa and Enceladus. This suggests that the definition of habitability may be much broader than previously thought, including varied scenarios that expand the boundaries of the possible. Thus, the third factor of the Drake equation leads us to reflect on the diversity of worlds. Science today suggests that a significant fraction of stars with planetary systems have at least one potentially habitable planet. This reinforces the notion that the galaxy may be full of environments where life, in its simplest or even more complex forms, could emerge. The next step is to investigate, among these habitable worlds, on how many life actually manages to arise, which leads us to the fourth factor of the equation. The fourth factor of the Drake equation dives directly into the mystery of the origin of life. On how many potentially habitable planets does life actually arise? This is perhaps the most enigmatic variable of the equation, because until today we only have a single confirmed example: Earth. All reasoning we make about the probability of life emerging on other worlds is based on this solitary reference point. For this reason, this factor is not only scientific but also philosophical, as it forces us to question whether life is a natural consequence of the laws of chemistry and physics, or whether it is an extremely improbable and rare event. On Earth, evidence suggests that life arose relatively early in its history. Studies of microscopic fossils and chemical traces in rocks indicate that simple organisms already existed more than 3.5 billion years ago. This means that after the formation of the planet and the initial cooling that allowed the presence of oceans, life appeared in a geologically short interval of time. This data led many scientists to believe that given the right conditions, life may be almost inevitable. If organic molecules are present in comets, asteroids, and even in interstellar clouds, it is reasonable to think that basic biochemistry can develop in different cosmic environments. However, we still do not know whether this optimism is justified. The passage from chemistry to biology remains one of the greatest mysteries of science. The most accepted theories include the primordial soup hypothesis, in which chemical reactions in shallow oceans produced complex molecules, and the hypothesis of life coming from space, known as panspermia, in which microorganisms or chemical building blocks could have reached Earth through meteorites. In both cases, the big question is whether this process is common and replicable on other worlds, or whether it was an extraordinarily rare accident that gave us life. Laboratory experiments, such as the famous tests by Stanley Miller in the 1950s, showed that simple organic molecules can arise spontaneously in conditions that simulate the primitive atmosphere of Earth. This type of result feeds the view that life may be an emergent phenomenon in suitable environments. But without a second confirmed biosphere, whether on Mars, on a moon of Jupiter, or on an exoplanet, we still do not know whether Earth is the rule or the exception. The fourth factor, therefore, remains unresolved. It may range from extremely low values, if life is a rare event, to values close to 1, if it is almost inevitable in favorable conditions. At this point of the equation, we enter unknown territory, where science is still only beginning to explore. The future of astrobiology, with missions aimed at searching for signs of life on Mars, on Europa, or on Enceladus, may provide fundamental clues to reduce this uncertainty. Until then, this factor is both a scientific challenge and a source of reflection on our own uniqueness in the cosmos. The fifth factor of the Drake equation deals with an extraordinary leap in the evolutionary scale. Among the planets that harbor life, on how many of them does that life develop intelligence? This question is particularly complex because, once again, Earth is the only laboratory available for analysis. We know that life appeared early on our planet and that simple forms, such as bacteria, dominated the oceans for billions of years. However, the transition from unicellular organisms to complex multicellular beings took an enormous span of time, raising the question of whether intelligence is a natural destiny of evolution or merely a very unlikely historical contingency. In Earth's history, life flourished in an almost infinite diversity of forms, but advanced intelligence, capable of producing technology, appeared in only one species, the human being. Other animals such as dolphins, octopuses, crows, and elephants display signs of sophisticated cognition, but they did not develop tools that profoundly altered their environment or communication systems that could be detected over great distances. This suggests that intelligence is not an obligatory path of evolution, but rather one possibility among many. Natural selection seems to favor immediate adaptation to the environment and not necessarily the accumulation of abstract reasoning. On the other hand, some scientists argue that intelligence could be a natural consequence in stable environments rich in resources. Life tends to explore niches, and the ability to solve complex problems can become a powerful evolutionary advantage. If this is true, then perhaps the emergence of conscious beings on other planets is more common than we imagine. The human example may not be an exception, but just the first glimpse of a universal pattern. The debate remains open and full of uncertainties. Earth's evolution shows that intelligence arose late, and that for billions of years the planet harbored nothing but simple forms. This may indicate that even in fertile worlds, most life remains microscopic or restricted to non-intelligent forms. If this interpretation is correct, the value of this factor in the equation is very low. But if intelligence is a recurring advantage in diverse ecosystems, the number may be high, greatly increasing the likelihood of civilizations existing in the cosmos. Thus, the fifth factor of the Drake equation forces us to face the delicate question of our own rarity. Are we a cosmic accident, or the inevitable result of universal evolutionary processes? The answer does not yet exist, but future discoveries in biology, paleontology, and astrobiology may shed light on this unknown. The next step of the equation, however, goes further. It is not enough to have intelligence. It is necessary to ask how many of these intelligences go on to develop technologies that can be detected by us. The sixth factor of the Drake equation addresses an even rarer transition. Among the intelligent species that arise, how many develop technology capable of being detected over great distances? It is not enough to think of cognition or culture, because even if a planet harbors intelligent organisms, it is necessary that they manage to transform their mental capacity into technical advances that produce observable signals. For us, the most evident example is radio and television waves, emitted for just over a century by humanity, which escape Earth's atmosphere and travel through space, carrying the unmistakable signature of a technological civilization. This factor is surrounded by uncertainties. Many forms of intelligence may never surpass the stage of complex societies without reaching technologies of interstellar communication. Dolphins, for example, possess sophisticated brains and complex communication skills, but live in an environment that hinders the creation of fire and metallurgy, which limits technological development. On different worlds, evolution may favor aquatic, subterranean, or even biological forms that do not require technology to thrive. In such cases, even if conscious life is abundant, it could remain invisible to external observers. On the other hand, once a species reaches a minimal technological level, the development of communication tools may be a natural step. If a civilization discovers electricity, builds radios, or develops lasers, the possibility of emitting detectable signals becomes inevitable. The great doubt is whether this stage is frequently reached, or if most intelligences never surpass social, environmental, or biological barriers that prevent them from creating machines. At this point, the equation reveals its limitation. We have only a single example and cannot generalize with certainty. Another important point is that detectability depends not only on the existence of technology, but also on its nature. Our radio signals, for instance, are becoming increasingly weaker since modern communication is migrating to more efficient digital systems with less leakage. It is possible that highly advanced civilizations use forms of communication totally undetectable to us, such as quantum transmissions or methods we cannot yet imagine. This means that even if they exist, we may never be able to perceive them. The sixth factor, therefore, raises profound questions about our own trajectory. We have been emitting signals for just over a century, a tiny fraction of cosmic history. If this stage is rare, perhaps most intelligences never become visible. If it is common, the universe may be full of civilizations transmitting messages, without us yet having the sensitivity to capture them. This dilemma leads us to the seventh and final factor of the equation. How long do these civilizations remain technological before disappearing or becoming invisible? The seventh factor of the Drake equation is perhaps the most decisive of all. For how long does a technological civilization remain active and detectable before disappearing or becoming silent to the cosmos? This parameter is crucial because even if many worlds develop life, intelligence, and technology, if these civilizations have short existences, the chance of coinciding in time with them will be minimal. It is like trying to hear an echo in an immense space. If the intervals are too brief, the sound is lost before we can capture it. When we observe our own species as an example, we perceive the fragility of this equation. Humanity has emitted signals into space for just over a century, a negligible instant when compared to the cosmic scale. This means that, until now, our window of visibility to the universe is incredibly narrow. If we survive for thousands or millions of years, we may leave a lasting mark. But if we become extinct soon, whether due to natural causes, wars, climate change, or social collapses, our contribution to cosmic silence will have been almost imperceptible. This factor is closely tied to the concept of self-destruction. Many civilizations may reach the technological stage, but at the same time, this power gives them the ability to generate their own ruin. The mastery of nuclear energy, the predatory exploitation of the environment, or the creation of systems out of control may lead a species to collapse. This risk is known as the Great Filter, a barrier that prevents societies from advancing beyond a certain point. If the Great Filter lies ahead of us, the average longevity of technological civilizations will be low, drastically reducing the chances of contact. On the other hand, if a civilization manages to pass through this critical period of instability, it may reach stages of sustainability that allow it to exist for millions of years. Societies capable of colonizing other worlds, of harnessing energy in a balanced way, and of maintaining stable social structures could prolong their presence to cosmic timescales. In this scenario, even if the initial probability of their emergence is small, their enormous longevity would increase the chances of us detecting at least one of them. The seventh factor, therefore, concentrates the philosophical and existential weight of the Drake equation. It forces us to reflect not only on other civilizations, but also on the destiny of our own. If we survive long enough, we will become an active part of this equation. If we fail, we will be nothing more than a fleeting spark in the history of the galaxy. This variable closes the mathematical structure, but opens the field to even greater questions, such as the central enigma. If the chances are so numerous, why have we not yet found anyone? This is where the famous Fermi paradox emerges. The Fermi paradox is one of the most intriguing dilemmas of modern science and connects directly to the Drake equation. It can be summarized in a single question. If the universe is so vast and the chances of life seem so great, then where is everybody? This unease arose in the mid-20th century, attributed to the physicist Enrico Fermi during an informal conversation with colleagues. The logic is simple. If there are billions of stars in the Milky Way, many of them with habitable planets, and if life has a natural tendency to arise and evolve, then we should already have detected signs of other civilizations. The cosmic silence, therefore, becomes a profound enigma. This paradox intensifies when we consider the scale of time. The galaxy is more than 10 billion years old, while humanity is recent, with only a few thousand years of organized civilization. If other societies had millions of years to develop, it would be reasonable to expect that some would already have spread throughout the galaxy, colonizing neighboring systems or leaving traces of their existence. Yet until today, we have no solid evidence that this has happened. The apparent emptiness contrasts with the immensity of possibilities, creating an intellectual discomfort that challenges our assumptions. Several hypotheses have been proposed to explain this silence. One is that intelligent life is extremely rare, and that perhaps we are an unlikely exception in the cosmos. Another suggests that life may even be common, but the leap to advanced technology is exceedingly rare. There are also those who argue that civilizations tend to self-destruct before reaching a stage of interstellar expansion, which would drastically reduce their longevity. In this view, the Great Filter could be before or after us. Either we have already overcome it, or we still have to face it. Other hypotheses are even more intriguing. Perhaps civilizations are present but silent by choice, adopting a policy of non-interference. This idea is known as the zoo hypothesis, in which we would be observed without realizing it. Another possibility is that they communicate in ways so different from ours that we simply lack the means to recognize them. There is also the chance that the universe is full of signals, but that we do not yet have the technological sensitivity to detect them. The Fermi paradox is not just a mathematical provocation, but an invitation to rethink our own limitations. It reminds us that cosmic silence can be interpreted both as a sign of our solitude and as evidence of our ignorance. At the same time, it gives an even greater urgency to the scientific search. Every advance in telescopes, radio telescopes, and space probes may bring us closer to the answer. The paradox remains unresolved, and perhaps it is precisely in this mystery that its strength lies, for it keeps alive the question that drives us to explore. Are we truly alone? The so-called Great Filter hypothesis is one of the most intriguing attempts to explain the Fermi paradox. It proposes that, at some point along the evolutionary line that goes from the formation of stars to the emergence of advanced technological civilizations, there exists an almost insurmountable barrier that prevents life from progressing further. This barrier would be the filter, capable of drastically reducing the number of societies that reach a stage of interstellar communication. Thus, although the Drake equation suggests many opportunities for life to develop, the Great Filter would explain why, until now, the universe seems silent. This filter may be behind us or ahead of us. If it is behind, it means that the improbable step has already been taken. Life would have arisen in an extremely rare way, and we would be an almost miraculous cosmic exception. In this case, the absence of detectable civilizations would not be a surprise, since most planets would never have surpassed the stage of primordial chemistry. On the other hand, if the Great Filter is still ahead of us, the scenario is darker. Civilizations may arise frequently, but almost all end up disappearing before becoming long-lasting. This may occur through self-destruction, environmental collapse, wars, pandemics, or even through energetic and social limitations that prevent them from expanding. The idea of the Great Filter is provocative because it forces us to reflect on our own trajectory. The mastery of nuclear energy, global climate change, the intensive use of natural resources, and the creation of technologies that can spiral out of control are examples of risks that could limit humanity's longevity. If most civilizations face similar challenges and cannot overcome them, then the galaxy would become filled with sterile worlds that, at some point, hosted intelligent life, but ultimately fell into silence. At the same time, the hypothesis allows for cautious optimism. If we have already passed through the Great Filter, it means we have overcome the most improbable stage, and our task now is simply to ensure long-term survival. In this case, the fact that we are here would be evidence that we succeeded where countless other cosmic possibilities failed. However, if we have not yet reached this filter, we must develop maturity as a species to face it, creating a sustainable, resilient society capable of withstanding its own inventions. The Great Filter, therefore, is more than a scientific hypothesis. It is also a philosophical and existential warning. It reminds us that the survival of a civilization depends not only on its intelligence, but on the wisdom with which it manages its technology and environment. The cosmic silence may be a reflection of recurring failures of societies that did not manage to cross this barrier. It is up to us as humanity to decide whether we will be just another statistic in this universal filter, or whether we will succeed in overcoming it, remaining visible in the cosmos for thousands or millions of years. The SETI project, an acronym for Search for Extraterrestrial Intelligence, represents one of humanity's boldest and most persistent efforts to try to find signs of other civilizations in the cosmos. It was born alongside the Drake equation, precisely as a practical attempt to test its implications. The logic was simple. If there are technological civilizations in our galaxy, some of them could emit radio waves or other electromagnetic signals that would escape from their planets and travel through space, reaching us. All that was needed was the right technology to listen and interpret those messages. The first SETI experiments took place as early as the 1960s, using radio telescopes aimed at nearby stars. Although rudimentary, these attempts already revealed the ambition of listening to the universe as if searching for a needle in a cosmic haystack. Over time, the efforts became more sophisticated, expanding the sensitivity of the receivers and covering increasingly larger portions of the radio spectrum. Among the most celebrated moments is the so-called WOW signal, detected in 1977 by a radio telescope in Ohio. This strong and inexplicable signal, which lasted only 72 seconds, remains to this day one of the greatest enigmas of the search for extraterrestrial intelligence. Although it was never repeated, it fuels the hope that somewhere, someone may have tried to communicate. Over the decades, SETI has gone through ups and downs. Often criticized for not presenting concrete results, it has also been defended as one of the greatest intellectual adventures ever undertaken by humanity. The absence of confirmations does not necessarily mean that we are alone. It may simply indicate that we have not yet searched in the right way, in the right place, or for long enough. After all, the galaxy is immense, with hundreds of billions of stars, and the effort to scan the sky for signals is comparable to observing the ocean with a cup of water and concluding that there are no fish. Currently, SETI has gained new momentum with modern initiatives, such as the Breakthrough Listen project, financed by major private investors and supported by renowned astronomers. This new phase seeks to scan millions of stars and even neighboring galaxies in search of artificial transmissions. Beyond radio, there is also interest in exploring laser signals and other forms of communication that advanced civilizations could use. Each technological advance increases our chances of capturing something that might break the cosmic silence. More than a scientific experiment, SETI is a symbol of human curiosity and the courage to confront the apparent solitude of the universe. It reminds us that even without guarantees of success, the search for signals is an expression of the deep desire for connection. By pointing our radio telescopes at the sky, we are not only trying to listen to others, but also reaffirming our own identity as a civilization that looks beyond itself. in search of companionship in the infinite. The discovery of exoplanets, that is, planets located outside the solar system, has transformed the way we understand the universe and given new strength to astrobiology, the science dedicated to studying the possibilities of life in cosmic environments. Until the 1990s, there was no direct confirmation that other planetary systems really existed. Today we know that the Milky Way is full of them, with thousands of worlds already confirmed and millions of candidates. This advance changed the perception of the second and third factors of the Drake equation, showing that planets are abundant and that many of them occupy favorable positions around their stars. The great leap in this area came with telescopes such as Kepler and more recently the James Webb, which not only detected new worlds but also began investigating their atmospheres. This capability is revolutionary because it allows us to identify biosignatures, chemical signs that may indicate the presence of biological processes. The detection of oxygen, methane, or specific combinations of gases in an exoplanet may be evidence of organic activity. Although we are still in the early stages of this analysis, the perspective is clear. We are approaching the possibility of identifying signs of life in distant worlds without leaving Earth. Astrobiology is not limited only to exoplanets, but also investigates bodies within the solar system itself that present promising conditions. Mars, for example, once had liquid water on its surface and may still harbor underground microorganisms. Icy moons such as Europa and Enceladus hide liquid oceans beneath their icy crusts, heated by tidal forces, ejecting plumes of water into space that can be analyzed by probes. Titan, Saturn's largest moon, has methane lakes and a complex chemistry that may point to alternative life forms not based on carbon and water. Modern astrobiology has therefore radically expanded our vision of where to search for life. The concept of habitability is no longer restricted only to the traditional zone around a star. Subterranean environments, thick atmospheres, hidden oceans, and even toxic atmospheres are now considered possible laboratories for cosmic biology. This makes the universe a fertile field of experimentation in which life may take forms we are not yet able to imagine. Each discovery of exoplanets reinforces the idea that life is not an exclusive privilege of Earth. At the same time, astrobiology provides tools to interpret this scenario within the structure of the Drake equation. If we confirm the existence of biosignatures on other worlds, we will be drastically reducing the uncertainty of the fourth factor of the equation. This will bring humanity closer to the answer to the question that has always accompanied it. Are we alone, or are we part of an invisible cosmic community spread across the stars? The reflection on extraterrestrial civilizations is not limited only to their existence, but also to the way they could develop over time. One of the most famous models for thinking about this subject is the Kardashev scale, proposed in 1964 by the Russian astrophysicist Nikolai Kardashev. This scale measures the level of advancement of a civilization based on its ability to use energy, starting from the principle that the greater the access and control over energy resources, the more sophisticated the technology will be, and the greater the possibility of expansion. Kardashev defined three major levels. A Type 1 civilization is one capable of harnessing all the energy available on its home planet, including natural resources, solar energy, and geothermal energy. A Type 2 civilization can go further and use the total energy of its star, which would require technologies such as the hypothetical Dyson sphere, a megastructure that would surround the star to capture its radiation. A Type 3 civilization would be capable of controlling the energy of an entire galaxy, something far beyond our current understanding. At this stage, these societies would have virtually unlimited access to resources, being able to modify entire stellar environments. Humanity on the Kardashev scale has not yet even reached Type 1. According to estimates, we are around 0.7, since we can manipulate part of the planet's energy, but we are still far from harnessing its full potential sustainably. This means that, compared to a Type 2 or Type 3 civilization, we are practically invisible on cosmic terms. For astronomers, this realization is important because it helps to think about detectability. A society that controls the energy of its star would inevitably leave observable traces, such as changes in the brightness of stellar systems or artificial emissions detectable at great distances. Searching for signs of advanced civilizations, therefore, does not only involve capturing radio transmissions, but also looking for indirect technological signatures, such as anomalous variations in the brightness of stars, which could indicate artificial megastructures. There have even been controversial cases, such as the star KIC 8462852, also called Tabby's star, which displayed inexplicable brightness variations. Although natural hypotheses are the most likely, the possibility of artificial constructions was considered, showing how contemporary astrophysics takes even bold scenarios seriously. The Kardashev scale, while fueling imagination, also serves as a warning. It shows us that if we want to move forward on the path of long-lasting civilizations, we need to learn to manage our energy resources responsibly. Control of energy is both a sign of power and a risk, as it can lead to destruction if not balanced. Beyond science fiction, this scale reminds us that humanity's survival depends on how we deal with the challenges of the present, while looking toward a future in which perhaps we may one day become a Type 1 civilization. When we talk about extraterrestrial life, we almost always project what we already know: organisms based on carbon and dependent on liquid water. This view is natural, since all terrestrial biology relies on these two fundamental pillars. However, many scientists argue that limiting our search only to this pattern may be a mistake. The universe is vast and full of extreme environments where chemistry may follow different paths, giving rise to forms of life that we might not even recognize at first. This is the field of scientific speculation about life based on different chemistry. Carbon is special because it can form long and complex chains, essential for molecules such as proteins and DNA. But silicon, for example, is also capable of creating complex structures, though less stable at high temperatures. Some researchers suggest that in cold, silicon-rich worlds, silicon-based organisms could exist, with biological structures completely different from ours. In the same way, water, which is the universal solvent for terrestrial life, could be replaced in certain scenarios by liquids such as methane or ammonia, which present chemical properties compatible with biological processes at very low temperatures. One of the most fascinating examples within the solar system is Titan, Saturn's moon. There, the surface is covered by lakes and seas of liquid methane and ethane, with extremely cold temperatures. Some theoretical studies suggest that complex molecules could organize themselves in these environments, creating exotic life forms adapted to a chemical cycle completely different from that of Earth. Another example comes from icy moons, such as Europa and Enceladus, where subsurface oceans in contact with minerals may generate enough chemical energy to sustain microbial ecosystems without depending on sunlight. These environments show that life does not necessarily need Earth-like conditions to exist. The possible chemical diversity greatly expands the scope of the Drake equation. If life can flourish in alternative solvents and different molecular structures, then the probability of the fourth factor of the equation, the emergence of life, would become much higher. This means that instead of restricting our view to Earth-like worlds, we should open our minds to much broader possibilities. Extraterrestrial biology may not only be different, but perhaps even incomprehensible to our current parameters. This kind of reflection puts us before a philosophical question. To what extent are we prepared to recognize radically different forms of life? It is possible that we have already passed through inhabited environments without realizing it, precisely because we were only looking for patterns similar to our own. Life based on different chemistry reminds us that the universe may be more creative than we imagine, exploring evolutionary paths that go beyond terrestrial experience. Thus, by expanding our definition of life, we also increase our chances of finding companionship in the cosmos. When we think about extraterrestrial life, the natural tendency is to look toward distant stars and exoplanets in faraway systems. However, perhaps it is not necessary to go that far. The solar system itself already offers a series of intriguing candidates that may harbor some kind of life, whether present or past. This perspective is particularly fascinating because it involves worlds that are, in cosmic terms, within our technological reach, allowing probes and space missions to directly investigate their environments. The closest and most studied example is Mars. For decades, it has been the target of intense exploration because it presents clear evidence of a wetter past. Dry riverbeds, minerals that only form in the presence of water, and signs of ancient lakes suggest that billions of years ago, Mars had conditions much more favorable for life. Today, its surface is arid and inhospitable, but the possibility that microorganisms still survive underground, protected from radiation, remains one of the greatest questions of modern astrobiology. Missions such as the Perseverance rover are precisely searching for biochemical clues that may confirm this hypothesis. Another promising target is the icy moons of Jupiter and Saturn. Europa, a moon of Jupiter, hides beneath its icy crust, a vast liquid ocean kept warm by tidal forces caused by the planet's gravity. This environment may offer energy and chemical conditions for the emergence of microbial life. Enceladus, a small moon of Saturn, proved even more surprising by expelling geysers of water and organic molecules into space, detected by probes such as Cassini. These jets indicate the presence of an active subsurface ocean rich in chemical compounds that could sustain ecosystems. Titan, the largest moon of Saturn, represents an even more exotic case. With its dense atmosphere and lakes of liquid methane and ethane, Titan challenges our classical notion of habitability. Although it is unlikely to find life similar to Earth's there, some scientists believe that forms of life based on completely different chemistry could exist, adapted to the extreme conditions of cold and alternative solvents. Studying Titan is therefore a way to expand our imagination about the limits of biology. Beyond these bodies, other places in the solar system also intrigue scientists. Callisto and Ganymede, moons of Jupiter, may contain internal oceans. Venus, despite its infernal surface conditions, recently presented controversial signs of phosphine in its atmosphere, which sparked debates about the possibility of microorganisms living in high-altitude clouds. Although there is still no consensus, this discovery reignited the idea that life may arise in unexpected niches, even on apparently hostile planets. The search for life in the solar system is essential because it offers the chance to find a second biosphere. If we discover life, even if only microbial, on Mars, Europa, or Enceladus, we will have proof that the emergence of biology is not exclusive to Earth. This would revolutionize our understanding of the fourth factor of the Drake equation, showing that life may be a common phenomenon wherever minimal conditions exist. And if we confirm that different forms of life arose independently within a single stellar system, then the chances that we are not alone in the universe would multiply in an extraordinary way. The Drake equation is, in essence, a multiplication of probabilities, and it is precisely in this mathematics that its strength and also its fragility lie. Each factor of the equation represents a necessary step for a technological civilization to arise and become detectable. When we multiply these factors, we obtain an estimate of the number of civilizations existing in our galaxy. The detail is that some of these values are already relatively well known, such as the rate of star formation, while others, like the probability of life arising, remain largely speculative. This makes the equation less of a definitive answer and more of a tool to organize our questions and measure our ignorance. The mathematics involved has a peculiar characteristic. Small changes in a single factor can drastically alter the final result. For example, if we consider that the probability of life emerging on habitable planets is high, the final number of estimated civilizations may become on the order of thousands or millions. But if that probability is extremely low, the result may fall to less than 1, indicating that perhaps we are the only ones in the entire Milky Way. This extreme sensitivity shows how the calculation is not only quantitative, but also conceptual, reflecting different views on the rarity or abundance of life. Another important mathematical implication is the impact of the longevity factor of technological civilizations. Even if all other parameters are optimistic, if civilizations last only a short time, the final number will be low. Conversely, if only a few arise but those that do manage to survive for millions of years, the result increases. It is a kind of balance between rarity and duration. Thus, the equation shows us that it is not enough to look only at the initial conditions of life, but also at the ability of societies to cross critical periods and achieve long-term stability. This mathematics of cosmic probabilities forces us to reflect on different scenarios. In an optimistic version, we can imagine a galaxy teeming with civilizations, separated only by enormous distances. In that case, the cosmic silence could be explained by our own technological limitations, unable to detect subtle signals. In a pessimistic version, the calculation suggests that intelligent life is a very rare accident and that perhaps we are a solitary point amid billions of stars. Both possibilities are transformative, as they redefine the meaning of our existence. The value of the equation, therefore, does not lie only in the numerical result, but in the exercise of thinking probabilistically about the universe. It teaches us that every scientific discovery, every exoplanet identified, every organic molecule found in a comet contributes to adjusting the variables and refining the estimates. The mathematics here is less of a closed calculation and more of a dynamic process, updated as our understanding of the cosmos advances. In this sense, the Drake equation is not just an equation, but a permanent invitation to expand our scientific horizons. The Drake equation is not only a mathematical exercise, but also a mirror that forces us to reflect on the meaning of human existence in the face of the cosmos. Its philosophical dimension is as powerful as its scientific relevance, because the equation deals with the deepest question we can ask. Are we alone in the universe? If the calculation results in high numbers, this suggests that the galaxy may be full of civilizations, transforming our notion of uniqueness into just another chapter of a much larger cosmic narrative. On the other hand, if the numbers are low, perhaps we are an extraordinary rarity, which further increases the responsibility of preserving life and consciousness here on Earth. This ambiguity places us before two opposing but equally impactful visions. In the first scenario, we are not unique, and our species is part of an invisible cosmic community formed by intelligences we may never meet. In this case, human solitude dissolves into a universal belonging, even if silent. In the second scenario, we are solitary amid billions of stars, and this confers on us an immense responsibility to be the guardians of a rare and fragile flame, capable of keeping alive the only spark of consciousness confirmed in the entire galaxy. The philosophy contained in the Drake equation also touches on our identity as a civilization. It compels us to question not only whether others exist, but also whether we ourselves will be able to last long enough to be counted. When we think about the longevity factor of civilizations, we reflect on the risks we face as a species and the urgency of overcoming our internal weaknesses. The equation, in this sense, works as a reminder that survival is not guaranteed, but depends on ethical, political, and technological choices made here and now. Another fascinating aspect is how the equation expands our perception of time and space. It places us before cosmic scales in which a century of radio transmissions is irrelevant compared to billions of years of galactic history. This creates an existential paradox. Even if life is abundant, the temporal coincidence to encounter another civilization may be minimal. Thus, the equation teaches us humility, showing that our view is limited by a narrow window of space-time, and that understanding cosmic life requires patience beyond human measure. At its core, the philosophical dimension of the Drake equation reminds us that, regardless of the result, the question itself already transforms our way of existing. If we are alone, our rarity should inspire us to protect Earth and the life that flourished here. If we are not, the universe reveals itself as a shared stage, in which we are part of a collective storyline that transcends planetary boundaries. In either case, the simple act of calculating and reflecting already broadens our consciousness, connecting science and philosophy in the same horizon of meaning. The Drake equation is not only a mathematical exercise, but also a mirror that forces us to reflect on the meaning of human existence in the face of the cosmos. Its philosophical dimension is as powerful as its scientific relevance, because the equation deals with the deepest question we can ask: are we alone in the universe? If the calculation results in high numbers, this suggests that the galaxy may be full of civilizations, transforming our notion of uniqueness into just another chapter of a much larger cosmic narrative. On the other hand, if the numbers are low, perhaps we are an extraordinary rarity, which further increases the responsibility of preserving life and consciousness here on Earth. This ambiguity places us before two opposing but equally impactful visions. In the first scenario, we are not unique, and our species is part of an invisible cosmic community formed by intelligences we may never know. In this case, human solitude dissolves into a universal belonging, even if silent. In the second scenario, we are solitary amid billions of stars, and this gives us an immense responsibility to be the guardians of a rare and fragile flame capable of keeping alive the only spark of consciousness confirmed in the entire galaxy. The philosophy contained in the Drake equation also touches on our identity as a civilization. It compels us to question not only whether others exist, but also whether we ourselves will be able to last long enough to be counted. When we think about the longevity factor of civilizations, we reflect on the risks we face as a species and on the urgency of overcoming our internal weaknesses. The equation, in this sense, serves as a reminder that survival is not guaranteed, but depends on ethical, political, and technological choices made here and now. Another fascinating aspect is how the equation expands our perception of time and space. It places us before cosmic scales in which a century of radio transmissions is irrelevant compared to billions of years of galactic history. This creates an existential paradox. Even if life is abundant, the temporal coincidence to find another civilization may be minimal. Thus, the equation teaches us humility, showing that our view is limited by a narrow window of space-time, and that understanding cosmic life requires patience beyond human measure. At its core, the philosophical dimension of the Drake equation reminds us that, regardless of the result, the question itself already transforms our way of existing. If we are alone, our rarity should inspire us to protect Earth and the life that flourished here. If we are not, the universe reveals itself as a shared stage, in which we are part of a collective narrative that transcends planetary boundaries. In either case, the simple act of calculating and reflecting already broadens our consciousness, connecting science and philosophy in the same horizon of meaning. The possibility of extraterrestrial life, when debated through the Drake equation, is not limited to the scientific or philosophical field. It also touches deeply rooted religious and cultural dimensions of humanity. Since ancient times, different spiritual traditions have imagined the existence of celestial beings, often interpreted as gods, angels, or spirits from the stars. These narratives shaped rituals, beliefs, and values over the centuries, showing that the idea of not being alone has accompanied humanity since its origins. What modern science does is reformulate that same question in mathematical language, but the cultural impact remains just as powerful. From a religious perspective, the discovery of intelligent life on other worlds would raise delicate questions. For some traditions, it could be interpreted as confirmation that divine creation is vast and includes other forms of consciousness beyond the human one. For others, it could generate a shock, challenging interpretations that place humanity as the exclusive center of creation. Theologians from different branches already reflect on this theme, suggesting that extraterrestrial life would not deny faith, but rather expand it, revealing a universe even more complex and grand than previously imagined. Culturally, the prospect of life beyond Earth also has a profound impact. It has inspired arts, literature, and cinema for more than a century, giving rise to works that explore both fascination and fear in the face of the cosmic other. Those days, films, novels, and songs about alien civilizations are not just entertainment, but also metaphors for our own social, political, and existential dilemmas. Contact with another form of intelligent life, even if only as a possibility, forces humanity to rethink its concepts of identity, unity, and otherness. The Drake equation, by quantifying this possibility, serves as a bridge between science and culture. It transforms an ancient question into an object of modern debate, capable of uniting laboratories, temples, and artistic spaces in the same reflection. For some, extraterrestrial life would expand spirituality, showing that creation is universal and not limited to Earth. For others, it would be proof that science can dialogue with myths and traditions without necessarily canceling them out. In this sense, the cultural impact of the equation goes beyond numbers. It redefines how we perceive ourselves in the cosmos and how we project our relationship with the sacred and the imaginary. Thus, the religious and cultural implications of the Drake equation reveal that the question of life beyond Earth is not only a matter of statistics or astronomy, it touches the very heart of the human condition, dealing with beliefs, symbols, and narratives that shaped entire civilizations. Regardless of the answer, The search for companionship in the universe will continue to be one of the deepest driving forces of our culture, uniting faith, science, and art in the same journey of discovery. The future of space exploration is closely tied to the search for life in the universe and to the deepening of the questions raised by the Drake equation. In the coming decades, a revolution is expected in observation technologies and interplanetary missions, which may bring concrete answers to variables that today remain speculative. One of the most significant advances will be the growing ability to study the atmospheres of exoplanets with next-generation telescopes, such as the James Webb and its successors. These instruments will be able to identify biosignatures, that is, combinations of gases, such as oxygen, methane, and ozone, which may indicate the presence of biological processes on distant worlds. Beyond remote observation, the solar system will continue to be the main laboratory of practical astrobiology. Missions are being planned to directly investigate environments with potential to harbor life. The European Space Agency and NASA, for example, are already developing projects such as the Europa Clipper mission, aimed at studying Jupiter's icy moon, famous for its vast underground ocean. Another initiative is the sending of probes to Enceladus, where geysers expelling organic molecules have already been observed. These missions will not only seek signs of microbial life, but will also help us understand the habitability of icy worlds, expanding our concept of where life can thrive. The exploration of Mars will also continue to be a priority. The Perseverance rover is already collecting samples that are expected to be brought back to Earth in the future, enabling detailed analyses in laboratories. The confirmation of microbial fossils on Mars would be a historic milestone, proving that life arose at least twice within the same stellar system. This would drastically reduce the uncertainty of the fourth factor of the Drake equation, increasing confidence that life may be common in the cosmos. In the field of interstellar communication, new projects will seek artificial signals on even larger scales. Breakthrough. LISTEN already represents the largest continuous effort to search for extraterrestrial transmissions, but the future should include more sensitive radio telescopes and global networks capable of covering a larger fraction of the galaxy. In addition, there are proposals to send deliberate messages, an effort known as METI, which involves the active attempt to contact possible civilizations, although this theme divides opinions due to the risks associated with revealing our presence. Further ahead, humanity may take even bolder steps, such as building interstellar probes capable of traveling to nearby systems, such as Alpha Centauri. Conceptual projects like Starshot plan mini-probes propelled by laser sails, which could reach these systems in a few decades. Although still a technological challenge, this kind of initiative shows that we are entering an era in which exploration will not only be theoretical, but practical, with human machines visiting distant worlds. The future of space exploration, therefore, is also the future of the Drake equation. Each mission, each telescope, and each discovery will contribute to filling its variables with more concrete data. We are facing an era in which the age-old question about life in the universe may finally find answers. Whether confirming our cosmic solitude or revealing the existence of stellar neighbors, space exploration will forever transform humanity's view of itself and of the cosmos it inhabits. Since it was proposed in 1961, the Drake equation has undergone several revisions and adaptations, keeping pace with advances in scientific knowledge. In the beginning, many of its factors were practically speculations, based more on estimates than on concrete data. Today, however, some of these variables can already be calculated with greater precision, thanks to the discovery of exoplanets, advances in astrobiology, and new astronomical observations. This does not mean that the equation is solved, but that it has become an even more relevant tool to organize our constantly evolving understanding. The first factor, the rate of star formation, is now relatively well known. Our galaxy produces between 1 and 10 new stars per year. The second factor, the number of stars with planetary systems, was revolutionized by discoveries from the Kepler telescope and its successors, which confirmed that practically all stars have planets. The third factor, the average number of potentially habitable worlds, also became clearer, with estimates of billions of rocky planets in the habitable zone of the Milky Way. These advances show that the first steps of the equation are more optimistic than imagined in the past. The factors related to the emergence of life, the development of intelligence, and the creation of detectable technology remain highly uncertain. We have not yet found a second confirmed biosphere, whether on Mars, on icy moons, or on exoplanets. This keeps the fourth factor open, oscillating between the hypothesis that life is almost inevitable and the pessimistic view that it may be an extremely rare event. Similarly, the fifth and sixth factors still depend on conjectures, based only on the terrestrial example. The seventh factor, the longevity of technological civilizations, continues to be the most speculative of all, as it depends not only on science, but also on social, political, and ethical choices that determine the destiny of each species. Some scientists have proposed extended versions of the equation, adding variables such as the probability of civilizations actively communicating or the chances of detecting biosignatures in planetary atmospheres. Others argue that the equation should also include cultural factors, such as the tendency of societies to explore or remain isolated. These revisions do not invalidate Drake's original version, but expand its usefulness, transforming it into a flexible framework that can be adjusted as new information emerges. Revisiting the Drake equation today is to recognize both how far we have come and how much we still do not know. If the first factors already appear generous, the latter remain shrouded in mystery, reminding us that the question of life in the universe remains open. The equation is not just a mathematical formula, but a reflection of human curiosity and the evolution of science. Each revision makes it less speculation and more science, bringing us closer, step by step, to the answer to one of the deepest questions of existence. Are we alone or not? Imagining the impact of a first contact with extraterrestrial life is an exercise that combines science, sociology, psychology, and even philosophy. The mere confirmation that we are not alone in the universe would irreversibly change the way we see ourselves and the place we occupy in the cosmos. Throughout history, scientific discoveries that displaced humanity from a central position, such as the Copernican revolution or Darwin's theory of evolution, already generated profound shocks. But the revelation of another intelligent civilization would be incomparably more transformative, affecting every aspect of human life. The first impact would be scientific. The confirmation of an extraterrestrial civilization would validate decades of research and open a new era of exploration. Questions about the origin of life, the evolution of intelligence, and the biological diversity of the cosmos could finally be answered. If it were possible to establish communication, the exchange of knowledge could accelerate our technological development and expand the boundaries of our understanding. Even if the contact were limited to distant signals, the very existence of another intelligence would already redefine science as a universal endeavor, not just a terrestrial one. The cultural and psychological impact would be equally profound. Humanity would have to deal with the breaking of one of the greatest taboos in its history, the idea of being alone in the universe. For many, this could generate a sense of cosmic connection and belonging, reducing borders and nationalisms by showing that we are only a small part of a much greater reality. For others, it could cause fear, anxiety, and even resistance, since we would be facing something unknown and beyond our control. Literature and cinema have already anticipated these dilemmas, showing how contact with the other can be both inspiring and terrifying. In the religious and philosophical field, the discovery of another intelligent civilization would raise intense debates. Some traditions might see extraterrestrial life as confirmation of the grandeur of divine creation. Others might feel challenged in their narratives about the centrality of humanity. In any case, global spirituality would need to reorganize itself in the face of evidence that consciousness is not exclusive to Earth. This redefinition could generate both conflicts and renewals, depending on how different societies reacted to the new paradigm. The political and social impact also cannot be ignored. The news of a first contact would require international cooperation on a scale never seen before. No country alone could claim the privilege of representing humanity. This could encourage alliances and the creation of global protocols, but it could also generate tensions if there were disputes about how to deal with the new reality. In addition, the prospect of contact would raise questions about our own security. More advanced civilizations could represent a threat, or perhaps not care about us at all. Finally, the greatest impact would be existential. Knowing that we are not alone would force humanity to rethink its role in cosmic history. Our fragility, our achievements, and our conflicts would gain a new scale of meaning. We could finally understand that, in the face of infinity, the survival of the species and the care for the planet are even greater responsibilities. The first contact, whether with simple microorganisms on Mars or with signals from a distant civilization, would not be just a scientific event, but a revolution in the way humanity sees itself and the universe. When we reflect on the Drake equation and all the factors that compose it, we inevitably arrive at two great future scenarios. We are alone in the universe, or we are not. Each of these scenarios, although opposite, carries equally profound and transformative implications for the destiny of humanity and for the way we understand cosmic reality. In the first scenario, the loneliest one, intelligent life would be an extraordinarily rare phenomenon. Perhaps the fourth factor of the equation, the probability of life arising, is extremely low, or perhaps the great filter is positioned in such a way that few civilizations survive for long. In this case, humanity would represent a cosmic rarity, an isolated spark of consciousness among billions of stars. This conclusion, far from being discouraging, would impose on us an enormous responsibility. We would be the guardians of something rare and precious, the only ones capable of preserving and expanding the flame of intelligence throughout the universe. Being alone would not mean emptiness, but rather a call to cosmic responsibility. In the second scenario, the more populated one, intelligent life could be common and abundant, spread throughout the galaxy in multiple places. In this case, cosmic silence would not be a sign of absence, but the result of our limitations. Perhaps we do not know how to search properly, perhaps we are listening on the wrong frequencies, or perhaps civilizations are so different from us that we simply do not recognize their signals. If this scenario is true, the universe is like a great stage full of voices, and we are still learning how to listen. This would bring with it a sense of belonging and integration into a larger cosmic community, even if distant. There are also intermediate scenarios. It is possible that simple life is abundant, but intelligent life is rare, or that civilizations exist, but are so distant in space and time that we will never coincide with them. In this sense, the cosmos may be inhabited, but not necessarily accessible to our direct experience. This possibility places us before a universe that is rich, but also practically lonely, where consciousness may exist in many places, but without our having the means to establish contact. These future scenarios are not just exercises of imagination, they shape our present choices. If we believe that we are alone, the focus must be on ensuring humanity's survival and expanding our presence beyond Earth, making us a civilization capable of lasting for millions of years. If we believe that we are not alone, we must intensify the search for signals and prepare ourselves for the cultural, philosophical, and political impact of a possible encounter. In both cases, the Drake equation reminds us that the answer, whatever it may be, will forever transform the way we understand life, intelligence, and the cosmos. The Fermi Drake equation is not just a mathematical formula, but a mirror that reflects both our knowledge and our ignorance in the face of the cosmic mystery. Since it was presented in 1961, it has become one of the strongest symbols of the search for extraterrestrial life, uniting science, philosophy, and imagination in a single framework of thought. Its strength does not lie in offering a definitive number, but in organizing our questions, showing clearly where we have advanced and where we still remain in the dark. Above all, it is a tool for thinking about the universe and our role within it. Throughout the previous sections, we saw how each factor of the equation represents a fundamental stage: the birth of stars, the formation of planets, the emergence of life, the development of intelligence, the creation of technology, and the longevity of civilizations. Each variable opens up an entire field of study, involving astronomy, biology, geology, sociology, and even ethics. The equation is interdisciplinary by nature, reminding us that understanding life in the cosmos requires the union of different areas of knowledge. The greatest legacy of the Drake equation, however, may be that it forces us to reflect on ourselves. If the result is optimistic, the universe may be full of civilizations, and our challenge will be to learn to detect them and relate to them. If the result is pessimistic, then perhaps we are an extraordinary rarity, entrusted with preserving and expanding the flame of intelligence amid the silent vastness. In either scenario, the equation calls us to responsibility, to care for our own survival, to protect our planet, and to develop maturity as a species. The search for life beyond Earth continues, and each technological advance brings us closer to the answer. Telescopes, probes, and future missions are about to explore atmospheres, underground oceans, and artificial signals on scales never before imagined. Cosmic silence, as intriguing as it is not the end of the story, but part of an open process that may last for centuries. What matters is that humanity continues asking, investigating, and expanding its vision. Thus, the Drake equation remains an intellectual beacon, reminding us that the oldest question of all, are we alone, has not yet been answered. As science advances, this question will continue to inspire us, to unsettle us, and to guide us in the cosmic journey. Whatever the final answer, the very act of searching already transforms us, for it places us in direct dialogue with infinity. Before closing this video, I want to make you a special invitation. If you made it this far, it is because you truly have scientific curiosity and interest in the deep mysteries of the universe. That is why I ask you to leave your like, because it really helps spread this content to more people who also want to learn. If you are not yet subscribed to the channel, take this opportunity to subscribe and activate the notification bell. This way, you will not miss any of our upcoming long documentaries about science, the cosmos, and the great enigmas of existence. And I really want to read your opinion. Comment below where you are watching this video from and what you think about the Drake equation and the Fermi paradox. Your participation is essential to enrich this community and to continue this journey of knowledge.